Okay, now we will see next chapter, that is chapter number 6, temperature measurement. Introduction. Temperature is very widely measured and frequently controlled variable used in numerous industrial applications. In general, chemical reactions in the industrial processes and products are temperature dependent, and the desired quality of a product is possible only if the temperature is accurately measured and maintained. Further, it forms an important governing parameter in the thermodynamic and heat transfer operations like steam raising, gas turbines in power generations, and also in numerous propulsion systems. In addition, in the heat treatment of steel and aluminum alloys, temperature measurement and control plays a crucial role in incorporating the desired material properties in the finished heat treated products. The other areas where measurement and control of temperature is essential are plastic manufacture, nuclear reactor components, milk and dairy products, plant furnace and molten metals, heating and air conditioning systems, space shuttle components, blades of gas turbines, etc. A number of definitions of temperature have been proposed. In a layman's language, one could define this as the degree of hotness or coldness of a body or an environment measured on a definite scale. Another simplified definition of temperature is based on its equivalence to a driving force or potential that caused the flow of energy as heat. Thus, we can define temperature as a condition of a body by virtue of which heat is transferred to or from other bodies. Further, in the kinetic theory of gases and in statistical thermodynamics, it is shown that temperature is related to the average kinetic energy of molecules or atoms of which the material is made of. Finally, the definition of temperature in thermodynamic sense is based on the ideal Carnot cycle. According to this, it is defined as a quantity whose difference is proportional to the work obtained from a Carnot engine operating between a hot source and a cold receiver. It may be noted that there is a marked difference between the quantities temperature and heat. Temperature may be defined as degree of heat, whereas heat is taken to mean as quantity of heat. For example, a bucket of warm water would melt more ice than a small spoon of boiling water. The warm water in the bucket obviously contains greater quantity of heat than that in the spoon containing boiling water, but its temperature is lower than the boiling water. In fact, that is readily apparent if a finger is dipped in both the vessels. Temperature is a fundamental quantity, much the same way mass, length, and time. The law that is used in temperature measurement is known as the Zeroth law of thermodynamics. This states that if two bodies are in thermal equilibrium with a third body, then they are in thermal equilibrium with each other. In other words, all the three bodies would have the same temperature. Thus, if one can set up a reproducible means of establishing a range of temperatures, unknown temperatures of other bodies may be compared with the standard by subjecting any type of thermometer successively to the standard and unknown temperature and allowing thermal equilibrium to reach in each case. In other words, the thermometer is calibrated against a standard and is subsequently used to read unknown temperature. Temperature scales. Two temperature scales in common use are the Fahrenheit and Celsius scales. These scales are based on a specification of the number of increments between freezing point and the boiling points of water at the standard atmospheric temperature. The Celsius scale has 100 units between these points, while the Fahrenheit has 180 units. The Celsius scale is currently more in use because of the adoption of metric units. However, the absolute temperature scale based on the thermodynamic ideal Carnot cycle has been correlated with the Celsius and Fahrenheit scales as follows. Therefore, Kelvin, that is absolute temperature, Kelvin scale is equal to degree centigrade plus 273.15, where degree centigrade Celsius is temperature on Celsius scale. R is equal to absolute temperature or Rankine scale is equal to degree Fahrenheit plus 459.69, whereof F is the temperature on the Fahrenheit scale. The 0 points on both the scales represent the same physical state, and the ratio of two values is the same regardless of the absolute scale used, that is T1 by T2 Rankine is equal to T1 by T2 Kelvin. The boiling and freezing points of water at a pressure of 1 atmosphere, that is 103.3, 101.3 kilonewton per meter square, are taken as 100 degree and 0 degree on the Celsius scale and 212 degree and 32 degree on the Fahrenheit scale. The following relationships between Fahrenheit and Celsius and Rankine and Kelvin scales can be easily derived. That is degree Fahrenheit is equal to 32 plus 9 divided by 5 degrees Celsius, and Rankine is equal to 9 K divided by 5 degrees Celsius. With SI unit, the Kelvin temperature is measured. Therefore, always remember temperature is measured in degrees Celsius and then it is converted into Kelvin. That is the SI unit by adding 273 to the degree Celsius. Now this international practical temperature scale. To enable the accurate calibration of a wide range of temperatures in terms of the Kelvin scale, the International Practical Temperature Scale IPTS 68 has been devised. The list 11 primary fixed points which can be reproduced accurately. Some typical values are primary fixed points, first column, second temperature Kelvin, third temperature degree Celsius. First is triple point of equilibrium hydrogen, equilibrium between solid, liquid and vapor phases of equilibrium hydrogen. 13.8, here minus 259.34. Second boiling point of equilibrium hydrogen, 20.28 minus 252.87. Triple point of oxygen, 54.36, here minus 218.78. Boiling point of oxygen, 90.18 minus 182.96. Triple point of water, 273.16.01. Boiling point of water, 373.15, 100. Freezing point of zinc, 692.73, 419.58. Freezing point of silver, 1235.58. This is 961.93. Freezing point of gold, 1337.58. Temperature, here degree Celsius, 1064.43. In order to establish a scale completely, a means of interpolation between the fixed points is required. Resistance thermometers are used for this purpose for temperatures below 630 degrees Celsius and thermocouples between 630 and 1064 degrees Celsius. And above this temperature range, radiation methods are used to extrapolate the scale. Apart from the primary standard points, there are 31 secondary points on the International Practical Temperature Scale, which forms the convenient working standard for the workshop calibration of the temperature measuring devices. Some typical values of these points are given in table. Therefore, secondary points, sublimation point of carbon dioxide, first column is, the second column is temperature in Kelvin, third column is temperature degree Celsius. 194.674 minus 74.47. Freezing point of mercury, 234.28 minus 38.86. Equilibrium between ice and water, that is ice point, 273.15. 0. Melting point of bismuth 554.59, 271.44. Melting point of lead 600.65, 327.50. Boiling point of pure sulfur 717.82, 444.67. Melting point of antimony 903.87, 630.74. Melting point of aluminum 933.52, 660.37. Melting point of copper 1357.6, 1084.5. Melting point of platinum 2045, 1772. Now measurement of temperature. Therefore, temperature cannot be measured directly, but must be measured by observing the effect that temperature variation causes on the measuring device. Temperature measurement methods can be broadly classified as follows. First, non-electrical methods. Second, electrical methods. And third, radiation methods. Now, first is non-electrical methods. The non-electrical methods of temperature measurement can be based on any one of the following principles. First, change in the physical state. Second, change in the chemical properties. And third, change in the physical properties. Therefore, as mentioned before, the temperatures at which a number of pure substances change their physical states are used for the calibration of temperature scales. But these devices give one particular value of a unique temperature corresponding to the change in the state of the substance. Hence, these are not suitable for measuring a range of temperatures. Further, for using the change in chemical properties, we have to look for a reversible chemical process in order to obtain a repeatable or reproducible scale with respect to change in temperature. However, such processes are very few in nature, and thus this principle of temperature measurement is hardly used. In fact, most non-electrical methods of temperature measurement are based on the change in the physical property, namely the same thermal expansion due to the change in temperature. These devices have electrical connections, therefore they are commonly used in areas where there is a risk of explosion, for example, to provide display of temperature in petrol storage tanks, etc. Further, although the magnitudes of expansion in such thermometers is very small, yet they produce enough power for direct operation of the mechanical. Now, first is the bimetallic thermometer. This type of thermometer also employs the principle of solid expansion and consists of a bimetal strip, usually in the form of a cantilever beam. This comprises strips of two metals having different coefficients of thermal expansion, welded or riveted together so that relative motion between them is prevented. An increase in temperature causes the deflection of the free end of the strip as shown in figure. Assuming that metal A has the higher coefficient of expansion, the deflection of the temperature is nearly linear depending mainly on the coefficient of linear thermal expansion. Invar is commonly employed as the low expansion metal. This is an iron and nickel alloy containing 36% of nickel. Its coefficient of thermal expansion is around 1 divided by 1/20th of the ordinary metals. पलीकडे हा लाल बटन आहे बघा लाल समोर ते काय लाल बटन आहे तिथे हात आहे तुमचा तिथं हा लाल बटन लाल बटन अलार्म लिहिले की तिथं Brass is used as high expansion material for the measurement of low temperatures, whereas nickel alloys are used when high temperatures have to be measured. A plain bimetallic strip is somewhat insensitive, but the sensitivity is improved by using a longer strip in a helical form as shown in figure. Therefore, this is bimetallic helix thermometer. One end of the helix is anchored to the casing and the other end, which is free, is conveniently connected to the pointer, which sweeps over a circular dial graduated in degrees of temperature. In response to the temperature change, the bimetal expands and the helical bimetal rotates at its free end, thus turning the stem and the pointer to a new position on the dial. The length of the stem may be up to about 0.6 meter, allowing the bimetal element enclosed in a protective sheet to be submerged in a hot substance without the indicator itself being subjected to excessive temperatures. Bimetallic thermometers are usually employed in the range of -30 to 550 degrees Celsius. Inaccuracies of the order of plus 0.5 to plus minus 1% of full scale deflection are expected in bimetallic thermometers of high accuracies. In addition to temperature indication, bimetal elements find a wide range of applications in the combined sensing and control elements in temperature control systems, mainly of the on-off types, that is thermostats. Movement of the strip has sufficient force to actuate the control switches employed in domestic ovens, electric irons, car winker lamps, and the refrigerators. In addition, these devices are also used as compensating elements for the ambient temperatures in the pressure thermometers, aneroid barometers, and as balanced wheel compensators in some watches. Therefore, this is the bimetallic thermometer and this is the bimetallic helix thermometer. Bimetallic thermometer, it consists of two different materials having different coefficient of linear expansion or thermal expansion. The bimetallic strip has the advantage of being self-generating type instrument with low cost, practically no maintenance expenses, and stable operation over extended period of time. However, its main disadvantage is its inability to measure rapidly changing temperatures due to its relatively higher thermal inertia. Next is the liquid in gas thermometer. The liquid in glass thermometer is one of the most common temperature measuring devices. Both liquid and glass expand on heating and their differential expansion is used to indicate the temperature. The lower temperature limit is -38.8 degrees Celsius for mercury down to -1300 degrees Celsius for pentane. The higher temperature range is 3400 degrees Celsius. Boiling point of mercury is 357 degrees Celsius, but this range may be extended to 5600 degrees Celsius by filling the space above mercury with N2 at higher pressure, thereby increasing its boiling point and range. The precision of the thermometer depends on the care used in calibration. A typical instrument is checked and marked from 2 to 5 reference temperatures. Intermediate points are marked by interpolation. The calibration of the thermometer should be occasionally checked against the ice point to take into account the aging effects. Precision thermometers are sometimes marked for partial or total immersion and also for horizontal or vertical orientation. The accuracy of these thermometers does not exceed 0.1 degrees Celsius. However, When accuracy is required, increased accuracy, a Beckman range thermometer can be used. It contains a big bulb attached to the very fine capillary. Range of the thermometers is listed to -5 to -6 degrees Celsius with an accuracy of 0.005 degrees Celsius. Liquid in glass thermometers have notable qualities like low cost, simplicity in use, portability, and convenient visual indication without the use of any external power. However, their use is limited to certain laboratory applications. It is not preferred in industrial applications because of its fragility and its lack of adaptability to remote indication. Further, it introduces time lag in the measurement of dynamic signals because of relatively high heat capacity of the bulb. Now we'll see these pressure thermometers. Pressure thermometers is used on the principle of fluid expansion due to an increase in the pressure in a given volume of the temperature measuring system. It is one of the most economical, versatile, and widely used devices in industrial temperature measurements. It has a relatively large metal bulb, often stainless steel, instead of glass. This results in a robust, easy to read thermometer that may be read remotely by connecting the bulb to a bourdon gauge or any other pressure measuring device by means of a capillary as illustrated in figure 6.3. The entire assembly of the bulb, capillary and gauge is calibrated directly on the basis of pressure change corresponding to the temperature change. The bulb of the thermometer may be filled with either a liquid or gas or a liquid vapor mixture, and depending upon the type of fluid, the thermometer is termed as mercury in steel thermometer or constant volume gas thermometer or pressure vapor pressure thermometer respectively. Fluid expansion thermometers are low in cost are low in cost, self-operated type, rugged in construction with no maintenance expenses, stable in operation and accurate to plus minus 1 degree Celsius. Further, the response of these instruments can be increased by using a small bulb connected to an electrical type of pressure sensor connected through a short length of capillary tube. And now this last thermometer will see mercury in steel thermometer. The mercury in steel thermometer has a linear scale. Sufficient power is available to operate a recording pen if required, as the total expansion of mercury is dependent not only on the bulb temperature but also on the temperatures of the capillary tube and bourdon tube. The system is subject to ambient temperature errors. Further, the magnitude of these errors depends on the ratio of the volume of mercury in the capillary at the measured temperature to the volume of the bulb. A reduction of the error is obtained by making the sensing bulb volume considerably greater than that of the capillary and bourdon tubes. This is inevitably increases This inevitably increases the thermal capacity and hence the thermal lag. The bulb size is therefore a matter of compromise. The volumes of the capillary and bourdon tube are made as small as transmission distance, and the required size of display could allow. Pressure thermometers are often connected with long capillary connecting tubes for remote measurements of the order of 100 meter. Ambient temperature error may be reduced by suitable compensation techniques. One arrangement uses a second bourdon tube and capillary, so arranged that the effect of ambient temperature change in this compensate system corresponding effect in the measuring system. Another potential use of error is the change in pressure head. which is introduced by any change in the relative levels of the bulb and the display. If the bulb is raised by high TH from the calibration level, then Gordon gauge experiences an increase in pressure equal to rho GH. This increase in level introduces an error in the indicator. This error is constant for any specified relative position of the bulb and display and may be removed by means of the zero adjustment of the indicating mechanism. The temperature range over which mercury in steel thermometer may be used is -25 to 550 degrees Celsius when the mercury is filled under pressure in the steel tube. Therefore, today we will stop here.